All right, we are here, Technology Fundamentals, Course 3, Session 2 on bagging, otherwise known as bootstrap aggregation. We will define that in a moment. Decision trees and random forests. So decision trees, a type of weak learner. We're going to define all this below. And random forests, an ensemble learning method that consists of decision trees, falls within the domain of bagging, a type of ensemble learning method. All right, we're going to define all these words throughout the notebook. In this session, we're going back to the topic of supervised learning models. So yesterday, we talked exclusively about how to engineer features, how to do pre-processing on our data set before we feed it into a machine learning model. Today, we're focused again on supervised learning. The last time we talked about this was in our regression and descriptive statistics notebook last week on Monday. All right. Bagging is an ensemble learning method. In this method, many weak classifiers cast their votes in a general election for the final prediction. The weak learners that random forests are made of are called decision trees. All right, starting with some standard imports. Should have seen all of this by now. We're going to use the random forest classifier from sklearn, specifically in their ensemble library. Should make sense since we just discussed that this is an ensemble learning method. Importing our truffle data set. Again, we've seen this before. And we're going to recreate the same operations we employed yesterday in feature engineering, splitting the data set into categorical columns and numerical columns. For the categorical columns, we're going to one-hot encode them. We're not going to do anything to our numerical columns, which happens to just be the kilograms. And then we're going to concatenate these two different types of data to create our final data frame, data object. And our target values will be the rate of production, or the margin normalized by quantity, the EBITDA per kilogram. For this classification task, we're going to identify high, medium, and low value products. So we're dividing the data up by its quantiles. Everything below the 25th percentile quantile will be marked as low. Middle will be 25 to 50, medium greater than 50, 50 to 75, and then high will be greater than 75. When we look at the histogram of these four different segments, we see that the number of observations in each one are the same. Makes sense, right? We've simply defined these groups by the quantile. So the number of observations in each group should be the same, about the same. Make sure I've ran all this up above. All right. And now I'm just adding this to my data frame. So we had the different categories: base cake, truffle type, primary and secondary flavors, color groups, the customer who ordered, the date of the order, the amount per order, the final profit margin, our profitability of high, medium, low, and bad. Bad is what we're giving the name for the really low stuff, below the 25th percentile. And then our profitability encoding. So we're going to assign numerical values to each of these. This is what we did with the dictionary here, class profit, 0 to 3. 3 being high, 0 being bad. We're going to use those numbers for our classification task. Decision tree. So we're going to start with that simple weak learner that we use to make a random forest. That weak learner is called a decision tree. In essence, a decision tree is a series of binary questions. Yes and no questions. That's what I mean by that. Yes and no questions about the data. All right, and we're going to see this in practice down below. To play with decision trees, I'm going to import from sklearn this library called tree. I'm going to make up some X data first instance will have the observation 0, 0, and the second will have 1, 1, and the targets for each of those is going to be 0 and then 1. And I'm going to construct my decision tree. So decision tree classifier is in the tree library. I'm going to set this equal to a variable, just like we've seen in the past. Again, should be becoming familiar with this. Once I have my object defined, I can call the .fit method on my data to fit the model. After fitting the model, we can use the predict method to show the output for a sample. So let's see what happens when I put 0, 0 here. Our output is 0, 1, 1, our output is 1. Looks like with 0, 1, its output is 1. With 1, 0, the output is 0. Okay, so we're just looking at what our model's doing. We didn't cover Gaussian mixture models in class, but this was left as an enrichment topic, an enrichment notebook for us to look at on our own. But just as with Gaussian mixture models, we can assign a probability of the outcomes. So let's start with 0, 0. And this is telling us that it's 100% probable that it will assign 0 as a target and 0% probable that it will assign 1 as a target. Same here. Here we flip that probability to assign absolutely the 1 label. All right, so this simple, this very simple data set that was used to train this very simple model has very unambiguous probabilities. It's giving 100% one way or the other. But we're about to look at something a little bit more complex in terms of the data. Interpreting a decision tree. Throughout today, we will discuss many ways to view both a single tree and a random forest of trees. Again, we're going to define random forest when we get there. One way to visualize these is a node and branch diagram. And we can visualize these or create the node and branch diagram by accessing the tree library, calling the method plot tree, and just providing the model. We can look at the decisions that are being made in the tree. So this top node is seeing all the data is passing through this top node. And it's taking the feature indexed at 1. So we're looking at our x values here. The feature indexed at 1 will be this for observation 1 and this for observation 2. And it's asking, is it less than or equal than 0.5? If it's less than or equal than 0.5, pass through the left, otherwise pass through the right. The Gini score we'll talk about in a moment. The samples is telling us the number of samples that are passing through this node from the training data set. In this case, all the data passed through the first node, which was just a whopping total of 2 samples. The value tells us the count for each place here. So this first number is telling us how many observations were labeled with 0, and the second number is telling us how many observations were labeled with 1. So you can think of this as just the count that is passing through each label. All right, so 1 is labeled 0 and 1 is labeled 1. When we pass to the left, we only have 1 sample that's gone through here because we only had 1 sample with a target value of 0. And we're seeing that come up in the value assignment below. And then the same but opposite with the right-hand side node. 1 sample passing through with the target value of 1, and we're seeing that in this value list here. To make this a little bit more clear, we can look at y itself. And our labels are actually 0 and 1. And when we're going through here, the number that is appearing left of the comma is representing the count of observations with the classification of 0, and the number right of the comma is telling us the count of observations with the classification of 1. All right, we also have a library called GraphViz that makes prettier diagrams. Same information again, but now the diagram is just kind of looks a little nicer. And now to talk about the Gini label, also known as Gini impurity, is a measure of how often a sample passing through the node would be incorrectly labeled if it was randomly assigned a label based on the proportion of all labels passing through the node. So in a sense, it is a measure of the progression of our tree. We're going to take an example on this. So I'm going to make some more fake data. I'm going into sklearn.datasets, importing a method that will generate data for me. I'm seeding it with the random state so that this is reproducible. When we look at the shape of X, we see that there are 100 observations with 20 features and 100 target values. When we look at the first 5 of the target values, we see that it's just a binary classification, either 0 or 1. And now we can train our tree. We're doing this the same way as before, grabbing the decision tree classifier blueprint, setting it equal to an object. Once we have the object, we can call the .fit method on our data. And now we can produce our tree. And just before we dig into defining the Genie and looking at the Genie label, let's talk about just the first layer of this tree. All the data is passing through this first node. 50% of the data has a classification of 0. 50% of the data has a classification of 1. And the question that we're asking at this node is at the 10th feature index, is that number less than 0.203? If it is, pass through the left. If it's not, pass through the right. Look at this next layer of nodes. We see that we've had a very efficient bifurcation of the data. In this node, only one label has a classification of 0 and 47 have a classification of 1. In this node, 49 have a classification of 0 and 3 have a classification of 1. So we have done a very effective bifurcation of the data just in this first node. As well as looking at the value, you can look at the number of samples passing through the second layer. 52 samples have passed through the left node and 48 samples have passed through the right. I'm going to stop there, but you should make it an exercise to look at the remaining nodes and determine for yourself whether these numbers make sense. But for now, let's just start with the first node. Can we confirm the observations in the tree by manually inspecting X and Y? So let's do this bifurcation. So I'm going to grab all the values in X, or rather just the first 10 values in X. I'm going to grab all the values in X, all the instances, okay? But only the feature indexed at 10. So I'm looking at the feature 10 of X, and I'm asking, is it less than 0.203? This is going to return the indices of where this is true, and then I can use those indices to index Y. And that's what I'm doing here. I'm indexing Y with that condition. And we see that when we ask this question, is feature 10 less than 0.203, the true, we get all these zeros. In fact, when we count these zeros, we should get 49, and we should get 3 ones. So I can go and look, there's a 1, there's a 1, there's a 1. I think there's only 3 ones. We might be able to do something like sum, perhaps, right? So if we sum this, we get 3. I don't know if we have value counts as a methodology in NumPy, no. Let's see, we could convert it to a series real quick. And the value counts. Right, so we have 49 zeros and 3 ones. Cool. We can confirm the Genie score of the top left node by hand. So I'm going to do just a test here 1,000 times. I'm going to run this test 1,000 times. And let's look at this list comprehension. So I'm going to create 52 data points, right? And I'm matching the number of samples that are passing through the node, right? 52 samples. And I'm saying 52 times. Remember, random.random is a uniform random number between 0 and 1. If that number is greater than 3 over 52, assign it a value of 0. Otherwise, assign it a value of 1. Where am I getting 3 over 52? 3 over 52 is the proportion of labels that have a 1 that are passing through the node. And this is the definition of the Genie score. If I were to randomly assign my label based on the proportion of labels passing through the node, what would my average score be for incorrectly labeling that data? So I can do this 1,000 times. What else is kind of unique about this? Y pred, I'm saying is my prediction. Y true, you'll notice I'm doing it the exact same way, right? And this is because it doesn't really matter what Y true is as long as it follows that proportion of our observations. This is how the test is kind of done, right? We're assuming that the data we see in the future is going to be of the same weighted distribution between 0 and 1. So I'm going to run this loop 1,000 times and return the mean squared error of Y pred and Y true. Then when I do this, I get an error rate of about 11%, which if we look at the Gini score for this node, we get 10.9 or approximately 11%. So I've just confirmed the Gini score that we're getting in the tree. All right, hopefully that makes sense. Let's take a look at this with our truffle data set. Vary the parameter max depth. What do you notice? Does the term greedy mean anything to you? Okay, so I see that when I declare my decision tree, I have this hyperparameter max depth. So I'm just going to set it equal to 1 to begin with. Look at the graph. All right, what is X4? So I'm saying, remember, we're classifying based on that bad, low, medium, high, right? So we have 417 observations in each class to begin with. And I'm asking, is feature 4 less than 0.5? Less than 0.5. Oh, and just as an error check for ourselves, does that Gini score make sense? I think it does, right? 75%. We're going to get the classification wrong 75% of the time if we're equally likely to label any data passing through to be one of the four categories. So 1/4 of the time we'll get it right, 3/4 of the time we'll get it wrong. So that's that Gini score of 75%. Okay, so is feature 4 less than 0.5? Passing through true, we see that we've gotten rid of some of the high levels, right? We've actually perfectly siphoned off 120 high scoring products. So let's look and see what is feature 4. So you can go into our encoder, or into our encoded features. So here's that encoder object we use to create our data. I just call get feature names, and then grab the 4th one, and it's our sponge. So here we're asking, is it a sponge cake? Yeah. And this is one great aspect of decision trees, their interpretability. We will perform this analysis again. For now, let's proceed with simpler data sets while exploring the features of decision trees. Before we move on, one quick note about this max depth. Let's do 2. So you notice what max depth is doing is allowing us to go further and further in our decision making, in our decision rules, right? Going back to Drake, we're going further and further. Each one of these Drakes is another layer. But something else that's important here, when I mentioned, does the term greedy mean anything to you? Notice that no matter what number I put this depth to, the preceding nodes don't change, right? So this first decision, we're always asking, is feature 4 less than 0.5? For this node on the left, we're always asking, is feature 18 less than 0.5, and so on. This doesn't change with the number of layers that we include. And this brings us to the definition of a greedy algorithm. A greedy algorithm doesn't optimize based on something in the future. It optimizes based on the current task at hand. So what you can take this to mean is that no matter where you're at in your tree, that current node is going to do its best to achieve the highest separation in the current data that it's viewing. Now, you can imagine that this will work in a lot of cases, but sometimes there'll be a decision that you want to make at the top of the tree that would make the decisions at the bottom of the tree a lot easier. We don't do this with decision trees. Decision trees are based on this greedy algorithm where we don't look into the future. So this is a quick side note there. All right, decision boundaries. We're going to make some blobs of data. Nothing crazy going on here. This is actually very similar to what we did with the data set up above, except now we have 2 dimensions we're looking at and 3 classes. So 2 different features, 3 different classes. Let's call up our classifier again, this time setting the max depth to 2. All right, so I'm calling my decision tree classifier max depth 2. I'm giving it a random state.
So for reproducibility. And when I do this, I get two decision boundaries. So one of these decision boundaries is made at the top of the tree in that first step, and then the other is made in the next layer. And we can see this down below. So in that first step, feature X1, we're asking, is it less than 5.746? Here's that decision line here. If it's not, it's giving it the classification of purple. There's 34 labels that are purple. Again, of course, these are numbers, but I'm just interpreting the colors here so we know what we're talking about. And then if we had only a single layer, these groups would be classified together because they would be at this node. But we have given the decision tree the ability to create another layer. So it then asks the question, is feature 1 less than -2087? And there's that decision boundary there. If it is less than that, give it the classification yellow. Otherwise, give it the classification of green. We can see from the output of this graph that the tree attempts to create the class boundaries as far from the cluster centers as possible, right? So we can see that here, the decision boundary is as far away between the centers of the clusters as possible. That's how we're seeing that. What happens when the clusters overlap? So I've created some data here where the blue or green and purple cluster centers overlap. And I'm going to write a wrapper for our plotting function so I don't have to rewrite this in our cells every time. And now when we look at our decision boundaries, you see that the boundaries mislabel some points, right? With just 2 layers, a depth of 2, we're not able to perfectly separate the data. So we're going to use this to motivate our conversation about overfitting in the context of decision trees. Let's increase the max depth. So now I'm going to do a max depth of 5. And we're going to train our model, look at the results. What we notice is that while the model accurately predicts the training data, we see some spurious labels, notably the trailing purple bar that extends to the otherwise green region of data here at the top. And this is a well-known fact about decision trees, that they tend to overfit their training data. In fact, this is a major motivation for why decision trees, a weak classifier, are conveniently packaged into ensembles. And this is, in fact, what we call random forests. We combine the idea of bootstrapping with decision trees to come up with an overall better classifier. We'll talk about bootstrapping in a moment. We have an exercise here, minimize overfitting. Repeat 413 with different max depth settings. Also read the docstring and play with any other hyperparameters available to you. What settings do you feel minimize overfitting? Let's just take this and we'll play with it. So there's a max depth of 4, 3. I think 3 actually probably does the best job. It seems most reasonable bifurcation of these centers. What are some other hyperparameters we might include? We can do min samples leaf. Maybe set this to 2. And now let's do add when we make the max depth really large. We notice that we don't get those weird corridors, right? We've increased the max depth, but we also say, hey, don't make a decision that only separates out a single observation. If I take this away, you see that we've made this decision boundary here based on one data point, but it leads to what would otherwise be some really weird labels going into the green region. That's another way we can regularize the decision tree. I think that's enough there. I'll leave it to you to peruse the docstrings. Random forests and bagging. What is bagging? Bagging, or bootstrap aggregation, is the process of creating subsets of your data and training separate models on them, and using the aggregate votes of the models to make a final prediction. Okay, so it involves having many different models, right? Many different models on many different subsets of your sampled data. And then we're going to take all of those individual models and have them vote on the final prediction. Bootstrapping is a topic in and of itself that we'll only touch on here without going through the statistical rigor of proof. Bootstrapping, or sampling from your observations with replacement,
simulates having drawn additional data from the true population. Very powerful technique. We use this method to create many new data sets that are then used to train separate learners in parallel. This overall approach is called bagging. So we have a little schematic here showing us the whole idea. We have an original data set right here at the top, and then we bootstrap this data set. We sample from it with replacement. So if I take this yellow dot here to draw a sample and place it here, I keep that yellow dot in the initial thing I'm sampling from. This is what we mean by with replacement. When I take it out to put it into my bag, I also leave it in there to sample from an additional number of times. All right, so the original data, we sample from it, and every time we take something from it, we don't actually take it out of the original population. We leave it there to be sampled again. This creates many different subsets of data that, what I mean by not touching on the statistical rigor of proof, it just so happens that when we do this, we get a better estimation of the population data. We're just going to take this at face value. Now that we have all those subsets of data, right, we can do this any number of times, is what we symbolize with the ellipses here. We then train a bunch of classifiers on those subsets of data, right? So we have all these individual classifiers or regression models, doesn't really matter, just some kind of machine learning model. And then once we have that completed, we aggregate the results. We use the output prediction from each one of these classifiers on a new observation to make the final prediction. We call that an ensemble classifier. A random forest is an instance of bagging where the separate learners are decision trees. So you can take this idea of original data, bootstrapping it, and then aggregating the output of a bunch of models. This is called bagging. The implementation of bagging, where decision trees are the weak learners in each one of these green boxes, is called a random forest. All right, random forest for classification. So I'm going to import my weak learner again from the tree library, and then from ensemble library, I'm going to import bagging classifier. First, I create my tree model, and then I feed that model into the bagging classifier. So you see here, very literally, I have created my weak learner here, and then fed it into the ensemble learner. So this is my weak learner, the tree, and my aggregation of the weak learners. I'm telling it here how many copies of that weak learner I want, 10. So 10 of these purple boxes, in other words. Max samples is the fraction of samples I want to be in each bootstrap data set. So that's this diagram here. And then I'm seeding a random state. And now I look at the output of that weak learner, or of that ensemble learner. In the above, we have bootstrapped by providing each individual tree with 80% of the population data. In practice, random forests can achieve even better results by randomizing how the individual classifiers are constructed. In fact, there are many unique methods of training individual trees, and you can learn more about them by following this link. For now, know that it is better in practice to implement the random forest method in sklearn rather than bag individual trees yourself. So this is a way we would construct a bagging ensemble learner if we wanted to do it ourselves, but sklearn, it's often better to just use the random forest classifier because they've done a lot of things under the hood to optimize how these individual learners play together. So we will typically always just use random forest classifier. And this is how I would do the same thing again now with the random forest classifier. All right, a little bit screwy if you ask me, this label right here in particular. It's trying to not mislabel any of the data points, and it's at the expense of what looks like overfitting. Interpreting a random forest. Let's revisit our truffle data set again, this time with random forests. So I'm going to declare my model, the number of estimators. Here I'm declaring the minimum number of samples I want in each leaf. And let's read this. We get a fairly high accuracy when our min samples leaf is low, and an accuracy that leaves room for improvement when min samples leaf is high. This indicates to us the model may be prone to overfitting if we are not careful. All right, so I get an accuracy score of 61% when my min samples per leaf is 6. And then we need to do some housekeeping to get back the names and categories that features were pulled from. So here I'm just doing some processing to get back the classification names from the one-hot encoded labels so that we can interpret our model. The feature importances are stored in CLF.featureImportances. These are calculated from the mean decrease in impurity, or MDI, also called the Gini importance. It is the sum of the number of nodes across all trees that include the feature, weighted by the number of samples passing through the node. One downside of estimating feature importance in this way is that it doesn't play well with highly cardinal features. What we mean by highly cardinal features are features with many unique values, such as mailing addresses. So if you have this feature where basically every observation has a unique encoding in that feature, your decision tree is going to use that many times to perfectly classify on your training data. It's going to overfit, and that highly cardinal feature is going to appear many times in your data set. So we're making note of that because we want to watch it here in this case. And now I'm going to use Plotly to create this chart. And we're going to ask, how does feature importance change when we change the minimum leaf size from 2 to 6? So here we're starting with 6. And let's just zoom in here on the top one. So we had things like base cake, the kilograms, primary flavor, right? So we're looking at these different features. Kilogram, what do we think about kilogram? There's a lot of unique kilograms in the data set, right? This is like the only floating point column we have. And so in this case, our minimum samples per leaf was set to 6. So maybe we are seeing that there's some importance of kilograms with overall profitability. But we want to be skeptical of this because in our data set, we have all class categorical features except for kilograms, and there's all these unique kilograms. And so this can be interpreted as a highly cardinal feature where basically it's like an address for a given observation. You can perfectly isolate the kilogram of a given order to then predict the margin for that order without finding a general rule across all the data. In other words, we're overfitting. Let's see what happens when we change this to 2. A little bit higher accuracy. And see the big change here. Kilograms jumped up to the most important feature, then followed by base cake, specifically singling out the sponge, the things made from sponge cake. Okay. What happens if we change this to 1? Kilograms spikes up even higher. And then we have the dates, right? So then the date starts to overshadow everything. And what do we think about that? Do we really think the date, based on our data hunt last week, I don't think we think the date is really going to be indicative of margin. But because there's all these unique date labels, we can use them further down in the tree once things have been separated by most of the other features. We can then separate them by date. And so date will appear in a lot of places, but at the bottom nodes of our tree. All right. Let's try this with a high number. Let's say we can only put 10. What is our accuracy? It goes down to 57%. Right, and so all of those features really get pushed out except for kilograms. But we see that the most important feature when we aren't allowed to isolate things for less than 7 samples is really the base cake type. Also, eggnog crops up there. Awesome. We can then go and look at the different EBITDAs when selecting for each of these features. All right. So now I just made a little interaction here, and I'm just selecting things that were base cake pound. So for things that were base cake pound, if they are base cake, if they do have the base cake of pound, they have an average EBITDA of 0.24, and if they don't have pound cake as their base cake, they have an average EBITDA of 0.19. You can look at eggnog. A little bit less of a difference for eggnog. Butter. I want to run this again, but let's do this. Let's do minimum samples per leaf is 1, so we're not really regularizing at all. Our accuracy jumps up to 100%, right? Because we're able to overfit. Most important feature becomes kilogram. And now let's look at our interactive plot this way. Oh, I'm not able to do this on continuous variables, right? Because I thing here is for classification. So let's just look at the dates. We see that with the dates, there really isn't a big difference in EBITDA, right? Not really. What this is telling us is that this split is just occurring sort of way down in the tree when everything else has been separated already, and it's just acting as a cardinal value. There's everything that appears in the leaf has a unique date, so they're able to split according to date, even though it's not truly indicative of our target, which is the rates. Let's try this again now with our regularized model. So let's try it with 6 as our minimum observations for the leaves. And now when we look at the top results from the Gini index, which is mostly the base cakes, we do get a meaningful split in rate when we look at the products with and without the indicated feature. All right, so sponge cake there, chiffon, eggnog, primary flavored donut. All right, so in conclusion, this is an example of how the interpretability of the random forest ensemble approach can be highly valuable, right? Random forest for regression. So up until now, we've been doing a classification task, but we can also use random forest for regression tasks. Because our labels on our blob data were numerical, we can apply and view the estimator in the same way. And now we just notice that our decision boundaries are non-binary, or they're not classifications necessarily. They are weights. I want to revisit a data set we brought up in session 1 rather, on feature engineering. Go ahead and change this. This was left as sort of an enrichment topic for us, looking at frequency or time to frequency domains. But we're going to see if a random forest regression model can capture the wave behavior of the time series data. I'm just creating my random forest here, 10 weak estimators, and I'm fitting to my frequency data. Blue is the original data, orange is the prediction. We see that we actually can fit really well. This without specifying any periodicity. The random forest does a good job of embedding this periodicity in the final output. Just showing the flexibility of random forest models, really cool. And as an extended exercise here, with the wine data set, predict quality or quality group, use train test split, create a learning curve of train and test score versus model complexity for your random forest models. And we'll leave that as an exercise.